here we go. I missed you guys so much. Oh my goodness. Okay, you can try this at home, although be careful. It's kind of dangerous. You might spill battery acid. But okay, so let's think about this for a second. So the battery is designed to give energy to charges. So if you take just a plain wire and you hook up the positive and the negative terminal of the battery, the idea is that, well, I'm going to do it the US way. The idea is that the charge, so pardon me, we know it's not really the positives, but the positives move through the battery, and as they move through the battery, they gain energy, electrical potential energy. So there they are gaining their energy. Now, in this circuit over here with the light bulb, they spend it from the light bulb. Okay, they spend it in the light bulb. So if this is a, most batteries are 1.5 volts, so that's 1.5 joules per coulomb. So remember, 1 coulomb, we talked about how like there's 1.9 times 10 to the negative 19th coulombs on 1 electron or 1 proton. So 1 coulomb of charge is a lot of individual charges. But so 1.5 joules, there's all this energy being held by those charges. And as it goes through this loop, it gets rid of it, and then it goes back to the battery, and it gets more energy, and it goes around and around. Gains energy, loses energy. Gains, loses, da, 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 da. It's just this loop that keeps going until the chemical reaction of the battery is exhausted. Okay, now I just have a wire, and we have a problem because the charges, the charges have all this energy, but they have nowhere to spend it. So what do? Where does it go? Energy is conserved. It's neither created nor destroyed. The energy is no longer stored in the chemistry of the battery. The energy is now hanging out here in the wire in these charge carriers, and it has to go somewhere, and it goes into heat, and the wire will get very hot. In fact, the whole dang thing will get very, very hot. In fact, you shouldn't do this because again, battery acid will come out. So if you were to do it, I would do it in a sink. But the whole battery and wire contraption will get hot enough that sometimes the battery will like unpeel, and that's called a short circuit, and that's generally thought of as a bad thing. Yeah. Oh, Angela's got a question. Sorry, guys. Wait, I stopped sharing. That's the problem. Okay, here we go. Okay, here we go. Okay, so the long and the short of it is that Ohm's law says that V equals I times R. So the voltage is 5 volts. The current is 0.5 amps. And the resistor, you may recall, was 10 ohms of resistance. And if I were to take different data points, in most cases I would get a straight line. I would put V on the y-axis. I would put I on the x-axis, and the slope would be my resistance. Okay, so let me just pause there for a second. Does that make sense? So I'll take my mouse and I'll change the battery here. So if I change the battery to 10 volts, for example, now the current is 1 amp because I would have 10 volts equals 1 amp times 10 ohms. And if I change it to 15, guess what? 15, this one's 1.5. So we've always got that linear relationship between voltage and current. And again, the slope is the resistance. So, yeah, slope is resistance. So that is the long and the short of the Ohm's Law lab. If I then, let's take a quick look at the questions that I had put in the lab. And I made a PDF of them just to make life a little easier here. Okay, so we set up the experiment. I only took 2 data points. My apologies. We made a graph, and then if we were going to write the equation, oh, I forgot. Can I do this? Yes. Yes. Okay. So this is the big takeaway. V equals IR, and R is the slope. If we get a nice straight line for our slope, we call it an ohmic material. Some materials, like light bulbs, are not ohmic because when they heat up, their resistance changes. But if we're working with a resistor, these little printed resistors, they're designed to stay constant. Oops. Okay. So what does the slope of the graph represent? You guys got it?
Resistor.
Resistance, yes. And then how about the y-intercept here? What would you guys expect the y-intercept to be in this situation? So again, same situation. Oops. Like when the voltage is 0, the current's going to be
0.
a 0. Yes. Oh, I got an answer in the chat. Absolutely. So the y-intercept should be 0 because that means it's not on. Okay. Oops. Oh no. I just did something. I'm too excited to see you all. I can't keep it all straight here. Who can blame me? Okay, let's see. Okay, we click on the resistor, we change the colored bands. The colored bands tell you the resistance. You don't need to memorize it. I just want you to be aware that those colors do tell you. If we were in class, I'd be like, you have to put them back in the drawer, in the right drawer, based on the colors, because that's what it is. And remember, the reason that they're like that is so I'm talking about these colored bands here. The reason that it's like that is because you can tell what resistor it is from any angle. Because these things get soldered into a integrated circuit, and then like if you printed it on one side and you soldered that side down, then you'd be like, what is that thing? I don't know. So that's the reasoning behind the colored bands there. Okay, let's see. We're doing pretty good, you guys. Doing pretty good. There's one more thing I want to say, and then then I'll try to stay true to my word of giving you something to look at. Okay, we talked about V equals IR. Last time, I believe we did finish these notes, but I recognize that it was a while ago. So let me see if this will work. All right. So I'm looking at the notes that we had talked about last time, or I don't know, you guys are so organized, maybe you can tell me. Do these look familiar to you somewhat? I know we went through this. We went through this guy with the funny cartoon. Um, this is one more formula that I just want to bring up again. The power formula. So power is current times voltage. And when you think about the definitions, this should make some sense. Current is charge per unit time, and voltage is energy in joules per unit charge. So what happens is the charges cancel and we end up with energy over time, and that's what power is. It's rate of energy consumption or rate of energy production. So I just wanted to remind you about that, and that power is measured in watts. We can take the power equation, and again, I think we did this, and combine these two equations. You get P equals, if you plug this in, you get P equals I squared R. And the other way you can combine it is P equals V squared over R. So with these three equations, well, with these combinations, the definition of power and Ohm's law, we can now figure out a lot of stuff. In fact, I bought my daughter a new computer, and we were looking at the power rating of the charger. It was a 45-watt charger, and it's plugged into a household circuit. So I could figure out the current that flows through that computer based on that power formula. And then once I have that, I could figure out the resistance of the computer as well. Okay, I'm going to stop talking at you. Thank you for bearing with me as I did all this.